the assumption is that the time it takes the sources to change is much smaller than the speed of light, which is equivalent to saying that if we thought about that time as the period of some oscillation, that the wavelength associated with the radiation is very large compared to the size of the source. Okay, so that's our assumptions about the nature of the distribution. And then we were looking at the fields in the so-called radiation zone when we are looking at it at distances that are big compared to lambda. That's the region in which the radiation dominates. So the dominant term in the multipole expansion is the electric dipole term, and the radiation associated with that, the electric field and the magnetic fields, are related to the second time derivatives of the electric dipole moment evaluated at the retarded time. Okay? And they are transverse to the direction of observation, which is radially out from the origin. And in the context of a harmonic oscillation with frequency omega, then what we see is the radiation is a spherical wave with an amplitude that is not isotropic because the fields must be transverse to the direction of propagation. Okay? And from that we discussed the notion of the differential power radiated into a particular solid angle, and that defined for us the so-called radiation pattern. Okay, and so for the example of a linear, this should be symmetric, it doesn't look that way at all. For the case of a linearly oscillating dipole, we have this so familiar dipole radiation pattern, sine squared, of the angle of observation relative to the direction of oscillation. And if we want to find the total power radiated, that gives us the Larmor formula, which we saw teaches us that the amount of power radiated depends on the acceleration of the charge. Okay? So I want to just quickly review, because I think things might have not been exactly clear last time, how we now are looking at higher order multipoles which radiate. Okay? If there is an electric dipole moment that is changing in time such that its second derivative is non-zero, that's the dominant effect. Okay? But there will be higher order corrections to that. Sometimes, as we know, as we see, the electric dipole moment is zero. And then, but we still can have electromagnetic radiation that is coming from the higher order multipole moments. Okay? Now we could do that in the way that we derived these expressions with the full expansion, which gave us the near field or the static zone and the induction zone and all those pieces. It's a giant mess to do that. So right now what we're doing is just restricting our attention to the radiation zone. Okay? And just looking at the multipole radiation in the radiation zone. And to do that, it is simplest to restrict our attention to harmonically oscillating sources. So we have made the assumption now that the charge density is oscillating with some frequency omega. And we know that any such function can be written in terms of the cosine and sine pieces, or equivalently the complex amplitude. And similarly, for the current density, okay? In which case, in the Lorentz gauge, the scalar and vector potentials are also oscillating with that same frequency. In which case, the retarded time solutions that we find are that the scalar potential is a superposition of spherical waves weighted by the strength of the source, and the vector potential is as well. Where I have used the shorthand here that K is equal to omega over C. All right? So at this point, we've made no approximations other than the assumption, which is not an approximation, that the sources have this form. This is the exact solution at this point for this kind of source. Now we are looking in the radiation zone. And in the radiation zone, we are restricting our attention only to the fields that fall off no faster than 1 over r. Fields that fall off faster than 1 over r correspond to either the intermediate zone, the induction zone, or the near zone, the static zone. So in that case, we can make the approximation. We're going to only keep terms that fall off no faster than 1 over r. So in that case, the only terms in the expansion that matter here is the 1 over r piece of that. And we can do an expansion of this in the approximation that r, the magnitude of x, is much, much bigger than the magnitude of x prime. In which case, this is approximately e to the I k r times e to the minus I k r hat x prime. Now, there was a little bit of a discussion yesterday. I wasn't quite, not yesterday, Tuesday at lecture, about what about the higher order terms in here. They will all go like faster when we extend that exponential out in a power series. You'll notice they'll have terms like x prime over, or the magnitude of x prime over r squared. So those terms do not contribute in the radiation zone. This is not about Fresnel versus Fraunhofer diffraction. That's another story which we'll get to later today perhaps, or Tuesday. This is about radiation from a localized source, where the localized source is small compared to the wavelength. Diffraction can have a very big slit that's much bigger than the wavelength of the radiation. It's a different set of approximations which we'll discuss in a little while. Okay? I got myself a little bit confused about that last time. So the higher order terms don't contribute to the radiation period. They contribute for the radiation in terms of the induction zone, etc. Okay, so this then looks like e to the I k r over r integral over all space dq to x prime rho twiddle x prime e to the I k minus I k dot x prime. Okay, where again, K is a shorthand for omega over C r hat. And this we recognize as the spatial Fourier transform of rho. So this then is equal to rho, or the Fourier transform as a function of k, e to the I k r over r. Similarly, we have the same expansion here that we did in the radiation zone. So this is in the radiation zone. And again, we see this is equal to the spatial Fourier transform of the distribution weighting strength of the spherical wave. So we have an extremely simple expression for the scalar and vector potentials when we're in the radiation zone, when the fields are oscillating harmonically. The scalar and vector potentials are proportional, are spherical waves whose strength depends on the Fourier components, the spatial Fourier components of the sources. Kind of nice. Now, one little aside over here, the spatial Fourier component of rho is related to the spatial Fourier components of J because of charge conservation. So what we know is del dot J plus d rho dt is 0. That is charge conservation. Okay. So when we are restricting our attention to harmonically oscillating fields, then that tells us that del dot J tilde of x minus I omega rho tilde of x is equal to 0. Okay, that's in the Fourier domain of time. Now if we take the spatial Fourier transform of this, every del becomes an ik, where this, of course, this is k r hat. So again, remember, I'm taking this Fourier transform respect. This is our k. K dot. Right now, this is an arbitrary k, but ultimately we evaluate it at this value of k. Now I'm just taking the Fourier transform. So that tells me that the spatial Fourier transform of this is equal to k over omega dotted into j. So if we now evaluate this at k equals omega over c r hat, then this equals r hat dotted into j as a function of that k over c. So what appears in the scalar potential is just the longitudinal part of j, the part that's along the direction of propagation, which is r hat. Okay, so this is equal to r hat, which is the same thing as k hat in this case, j over c, k r over r. Okay, so the longitudinal part of J gives rise to the scalar potential. Now we're looking for the fields. So the fields, E is minus the gradient of phi minus 1 over c dA dt. Okay? Again, we will take only, keeping only the radiation pieces, so only the parts that fall off like 1 over r and no faster. When we take the gradient of this, we'll only take the gradient of the exponent because the gradient of 1 over r falls off faster. That contributes to an induction zone piece. We're just going to ignore that for the moment. So the gradient then again becomes a multiplication by ik so that's the gradient of the scalar potential, and then I have to have a minus sign. Okay? And then we have the ADT. And the ADT is going to be, again, d by dt is minus I, so that's plus I omega over c is k times A, which is proportional to J. And all of this then multiplies e to the IKR over R. So what we find here is something very nice, which is that we have IK over C J minus R hat dotted into J tilde. This part came from the vector potential. This part came from the scalar potential. The scalar potential just subtracts off the longitudinal part, the part that's along the direction of propagation, so that the fields of radiation are transverse. So what we find is that the radiated field has a very compact, if perhaps convoluted form, but it's pretty compact, which says that the radiated electric field associated with a harmonically oscillating source in the radiation zone is the transverse part of the current density, the spatial Fourier coefficient associated with, at the value associated with k equals omega over 2 times r hat, the IKR over r. That's the transverse piece. Another way of writing that, if we can write that in terms of a triple cross product. Using the famous back minus cab rule. Right? Okay, what is the magnetic field? Well, the magnetic field is just del cross A, which is IK crossed into J, using the vector potential over here. C to the IK R over R, which is IK over C R hat crossed into J. And so we see, of course, that E and B are related. This is R hat cross E. E is equal to V cross R hat, which we must expect from the right-handed system of direction of propagation, E, V. E cross V is R hat cross E hat, etc. Assuming I got my signs correct, I hope I did. Okay, so far, this expression has not made a multipole expansion. It's just said we're keeping the radiation pieces and we have harmonic oscillation of our charges. Now we'll make a multipole expansion. Okay? So to do that, the multipole expansion just means expanding the spatial Fourier transform, which defines the strength of the field under the approximation at hand. Okay? So, now we can do a multipole expansion. So, the key player is the spatial Fourier transform of the current density. Which, under the approximation, remember that this, the exponent here, goes like kd. X prime is the distance from the origin to positions in the source, which are no bigger than d, which is kind of the order of the size of the source. So this is d over lambda, which is much, much less than 1. So now we make this approximation that this is small, we can then do a power series expansion. Okay? So we see here we're going to get moments of the charge distribution, in this case the current distribution, depending upon how many order we take. I'm going to change the notation slightly from what I did last time. Sorry. Let's call it now J0 instead of J1. So when n equals 0, that is the electric dipole approximation. The dominant effect in this small parameter. So that tells us J, called J0, is just the integral of that, which in the approximations that we've, not the approximations, but the manipulations we've used before, using integration by parts and all kinds of trickery like that, related to that, which then is equal to I omega times the electric dipole moment, using the fact that this is equal to I omega rho tilde from the expression that we have somewhere here. Right? There's a minus sign up. So, as that tells us that to lowest order, this spatial Fourier component is proportional to the first time derivative of the electric dipole moment. And as given over here, that tells us that the radiated electric field is equal to K squared P0 per e to the I K R over R, as expected. And B rad is K squared R hat cross P naught. All right, so the lowest order dominating term when K times B is tiny, meaning that the wavelength of the radiation is huge compared to the size of the source, is electric dipole. All right? Now let's look at the next order correction. So, n equals 1. So now we have to have the n equals 1 term here, and what we get is minus I, the integral over space k dot x prime j. So this is what I'm calling now j1. It's this spatial coefficient. First order expansion in this thing, j tilde of x prime. So let's look at some particular component of that vector. So that's the ith component of that. Just taking the ith component. And now use the Einstein summation convention. That becomes K sum over new dummy index, J. This factors out. That's K sub J E cubed x prime sub J, J tilde sub I. That's the integral we have to do. Okay? Sum over J gives us the ith component. So now we play some further trickery, and we break this outer product of two vectors, which is a tensor, into symmetric and antisymmetric pieces. So we write this as xj x prime minus the ith component, the j component, over 2. And the symmetric piece. Okay? So I've just broken up that tensor into symmetric and antisymmetric pieces. They add together to give this, obviously. Okay? When we do that, well, this part, as we will see in a moment, gives rise to magnetic dipole radiation, affectionately known as M1. And this gives rise to electric quadrupole radiation, affectionately known with great affection as E2. They contribute in the same order in the multipole expansion, as we will see. Well, we already kind of have seen that, but we'll understand what that means. What does it mean in terms of contributing in the same order, physically? So let's look at this term over here. So let's do a little aside over here. The integral x prime j, so I minus x prime sub I j tilde sub j, we recall is the dual of a cross product, meaning we can write this as epsilon ijk times the kth component of x cross j. Some ji. Okay, there was this relationship that we discussed early in the semester between n-symmetric tensors and cross products. Does this look familiar? What's that? That's a magnetic dipole moment. How quickly we forget. Well, kind of, there's a C in there, but that's okay. So this is equal to, remember the electric dipole moment, P is x times rho. And the magnetic dipole moment is x, it's just got a cross product. Everything in a magnetic field's got a cross product. So this is the C times the kth component of the magnetic dipole moment. Okay, its amplitude. That is to say, so when we put this together, the magnetic dipole moment contribution to the current we put these together, we get minus I, the j component goes over C, epsilon j I k, a different k, so j epsilon j I k m sub k, which is I over C, the ith component, this is the ith component, pardon me, ith component of this k cross m naught. Okay, so m as a function of t is the real part of m naught e to the minus t. That's the assumption. Everything oscillates like that. Okay, that looks just like what we had over here, except I've got some funky 1 over c's. I don't understand. It's not 1 over c, it's times c. Good. Because they have to have the same units. And so this is equal to ICK r hat cross n naught, which is I omega r hat cross n naught. All right? So, what we learned from this is that there is magnetic dipole radiation which is just given here. Well, this is already transverse. So this then, we have to multiply according to our formula over there. We take I omega over c squared, the transverse component of this guy, the M1 contribution e to the I k r over r. This is already transverse. So then this becomes minus omega squared over c squared r hat cross n naught e to the I k r over r. And the magnetic field associated with magnetic dipole radiation is equal to r hat crossed into E, which is equal to r hat crossed into r hat crossed into n naught e to the I k r over r, which is omega squared over c squared m naught per. So, what we learn here is that if we have a magnetic dipole moment, which is oscillating with frequency omega, then that will radiate, and the fields associated with that radiation look just like the fields, sort of, with some caveats I'll elaborate on in a moment, associated with magnetic dipole radiation, kind of switching the role of magnetic field and electric field, right? This is B naught perp, and this is, where is that? So let's review what I'm trying to say here. For electric dipole, if we have P double dot in this direction, and we look in the plane, here's r hat, this is the direction of propagation away, then what we have is that the electric field was like this, and the magnetic field was into the board, E cross B. Okay, so let me draw that more cleanly. B. K. Okay, so the magnetic electric field is in the plane of the oscillation and transverse component. For magnetic dipole, if we have m double dot in this direction, then what we have is, this is B, E is into the board, and this is R hat, which is K hat. All right? Now, what about the radiation pattern associated with magnetic dipole radiation? Well, it's exactly the same. I mean, these have exactly the same form. So if I have a linearly oscillating electric dipole, then what we saw is we had this kind of pattern with a sine squared theta strength of the differential power. Right? What's the differential power radiated in magnetic dipole radiation? Well, it's going to be equal to, from what we had before, of course, this is r squared times r hat times the mean Poynting vector, or the mean, not the mean, but the time average Poynting vector, which is going to be equal to r squared times c over 8 pi, the magnitude of, say, b squared, or e squared, it doesn't matter which one we choose. Doesn't matter. This then is equal to k to the 4th c over 8 pi, and not squared sine squared theta. The transverse component goes like sine theta squared. So it's exactly the same. So, for example, suppose I had a current loop, and I put an AC current on that current loop. It's a piece of wire. It's a neutral piece of wire. Does it radiate any electric dipole radiation? No, why not?
Because it's neutral?
Because it has no electric dipole moment. Right? There is no electric dipole moment for that current loop. The average position of the charge relative to the origin is 0. And it's always 0. It's not even changing. So there is no, if I just have a loop of wire and it oscillates current in it, it radiates though, and it radiates magnetic dipole radiation. If I have an antenna where I put current going up and down a wire, well, it's going to be dominantly electric dipole radiation. Now, if I have a distribution that has, say, both an electric dipole moment that's changing in time with a non-zero second derivative, and a magnetic dipole that's changing with respect to time that has a non-zero second derivative, well, then it will radiate both. But the dominant amount of power that's radiated is radiated into electric dipole radiation. How do we see that? So let's consider the problem that we're studying for homework, where I have two charges equal and opposite, say there's some distance between them r, that's rotating around at frequency omega. Does this distribution have a time-varying electric dipole moment? Sure it does, right? So it has the electric dipole moment as a function of time is equal to Q R is a function of t, okay, which is changing because it's going around in a circle. What about a magnetic dipole moment? What is the magnetic dipole moment again? I mean, we have this stupid cross product with the J's. But how do you remember for a loop, what is the magnetic dipole moment?
Oh, yeah.
Current, oh shit. So, so there is a current which is equal to the charge over the period, which is like Q omega, times the area. So this goes like this, right? Which goes like Q omega over C. That's good because it has the same units. Omega over C is 1 over length, so it's got the same units. Always a good check. So obviously. All right, so this is not the vector is out of the board. So I now ask you, what is the relative ratio of the power, total power radiated in electric dipole radiation versus magnetic dipole radiation? There will be a magnetic dipole radiation contribution to this, the radiation coming from this time-varying charge distribution. There will be an electric dipole contribution. What is the relative ratio between them? Well, we have that. The power radiated is proportional to the square of this moment, and for the case of electric dipole, it was exactly the same form with the magnetic dipole moment. So the ratio of these is the square goes like that square, which in this case is Q times that's like our D squared divided by Q omega over C times R squared. Which goes like 1 over omega C R squared. And omega over C goes like 1 over lambda. I really wanted it to do this, the ratio in the other direction. But what we see, let me write it as the other ratio, the power radiated in magnetic dipole compared to the power radiated in electric dipole, thus goes like R over lambda squared, which is our small parameter. In the whole multipole expansion was predicated under the assumption that the size of the distribution was small compared to the wavelength of the radiation, or said alternatively that the speed over which these things move is slow compared to the speed of light. In that case, the amount of power that's radiated in magnetic dipole is down compared to the amount that's radiated in electric dipole by the square of the small parameter. Right? Again, this is the same thing as R C over T, or the velocity squared. T being 1 over 3. Yes?
Does that actually have a magnetic dipole moment? Because it seems like since you've got, I don't know if you're thinking of it as like current or whatever.
You're right, there's two. Let's get rid of this guy.
Oh, I mean, that's
No,
like a good check
that's
mark.
important. No, you're right. Let's say it just had one charge.
Okay.
You're absolutely right, because it would cancel. Right, because one is positive, so but this still has electric dipole. This will still radiate. Excellent point, thank you. Exactly. I was noticed that before. Many years of teaching this course. You're absolutely right. But that does. And this is the main point. Okay? So, for example, if I were thinking about an electron moving around the nucleus in hydrogen, then if I have a certain distribution of charge associated with the electron cloud, as long as the electric dipole moment doesn't vanish, the electric dipole contribution to the radiation dominates. Why? Well, what is the speed of the electron moving around, sort of approximately, at least near the ground state? I thought about that from a kind of semi-classical perspective. Does anyone know? What's the ratio of V over C?
Alpha.
Yes. So in hydrogen, V over C is the approximately the fine structure constant, affectionately 1:137. And that's not so slow, but slow enough that the electric dipole contribution dominates. So we talk about dipole transitions in an atom, for example. All right. Let's now look at the next. There's still another piece of this that we haven't touched, which is, could it be more fun? And I mean fun, the electric quadrupole piece. Let's talk about that. So now let's talk about the electric quadrupole contribution. So the electric quadrupole contribution to the current, according to what we have over there, was equal to minus I k sub j times the integral dq mean dq x prime sub j tilde sub I plus x I, the j component, over 2. All right, so too many doodads on everything. All right, so let's read. All right, getting punchy here. Let's see, what am I doing? Oh yeah, so now we play the same tricks with integration by parts and blah, 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 and turn del dot j into rho, and we get this. Minus omega squared over c squared, factor of 2. The vector k, which is in the direction r hat, dotted into this tensor. Okay, where this is the outer product of x with itself. So there's a little bit of algebra associated with that that has to do with turning, using integration by parts and the tricks that we played before. This we recognize as the second moment of rho. It's related to the quadrupole tensor. Do you remember what the quadrupole tensor was? Maybe. So this, yeah, right. So let me write it down. Let's write it in this notation. That's the quadrupole tensor associated with that charge distribution, which is the amplitude. We're assuming, this is the complex amplitude list, we're assuming that this quadrupole tensor, as a function of time, is oscillating with this. What would be an example of such a thing? Suppose that I am a charge. I'm a charge distribution. I'm all positive charge. Maybe from your perspective, I'm all negative charge. I believe that can be. But I'm one charge. And suppose I oscillate like this. Gotta do those. Right? That's a quadrupole oscillation. Right? Because you remember that the quadrupole moment is the degree to which, if I have a single charge distribution, the degree to which it's non-spherically symmetric. And this is a quadrupole oscillation. I really didn't get any exercise today, so this is not so bad. All right. So that's an example of quadrupole oscillation. And if I were a charge, I would be radiating. And I know I'm radiating something at you right now. All right, so we don't have exactly that, but we have this thing then. Is equal to a third. I'm just going to call this is just a constant. This is just going to be real enough. A third Q naught plus the integral r prime squared Okay, so now what is the field associated with this in the radiation zone? Well, according to what we have to take the transverse part of this. The electric field associated with electroquadrupole radiation is the transverse part of this horrible mess. Horrible, horrible, horrible. However, well, R dotted in, this is the unit tensor. R dotted into the unit tensor is in the R direction. There is no transverse piece of that. So we only have to take the transverse piece of that. So that gives us minus omega squared over 6c squared, the transverse part of this vector. So R dot, the tensor is a vector, and we take the transverse component thereof. The magnetic field associated with this is equal to lost a factor somewhere. Oh yeah, there's that IK over C business. So this is, there's an I, there's an omega cubed, I got it right. Yeah, that looks right. All right, so, all right, that's what it is. Yeah. Let's look at the example of my knee bend squats. All right, so let's look at an example where Q0 is the following. It's some QD squared, say, times the matrix, which is the tensor representation in Cartesian coordinates, like this. You remember that the quadrupole tensor is a symmetric traceless tensor. That's this. This is the case of what we talked about at the beginning of the semester as a view, as the U-thou, symmetry. So this corresponds to a situation where I had, for example, you remember that problem we had for homework where we had the oblong nucleus and it had a quadrupole moment, and we did it for statics. Now the nucleus is becoming an egg on its side back to this, so it's going right? And radiating. It absolutely does. Have you ever listened to a nucleus? Okay, so that will radiate electroquadrupole radiation. What is the pattern associated with that radiation? Well, we have to look at the Poynting vector. What you do is look at the square of the amplitude. So we got to look at the square of the amplitude of this thing. So the differential power scattered, or not scattered, but radiated, is proportional to the square of something that couldn't be more pleasant to calculate. R cross bar dot divided into the tensor squared. That's the magnetic field squared. Right? Because that's the Poynting vector, and that's what the power is proportional to. So, we got to write this out. I'll bore you just a tiny bit with this. Maybe I've bored you more than enough for the semester, but we'll do it. Continue on. QD squared times minus a half XX plus YY plus ZZ, written out in outer product form. We got it, R hat is X over R is sine theta cos phi EX plus sine theta, sine phi EY plus cos theta EZ. That is the R hat vector expanded out in Cartesian components. This is the radial part, cylindrical unit vector in the XY plane. Okay? So now I got to take the dot product of Q with this. So R hat dotted into Q naught is equal to minus sine theta over 2 cos phi dx plus sine phi dy plus cos theta ut. That's the dot product between this and this. With the Q out front. So now I take the cross product of R with that. This is E sub phi again, E sub rho. So the cross product between those two R hat crossed into R dot Q naught is equal to QD squared times minus sine theta cos phi over 2 E Z crossed into E rho plus sine theta cos phi E plus Z. The cross product between the Z axis and the rho axis is the phi axis. Azimuth of phi, that's cylindrical coordinates. So, this whole business is equal to, and this is, all the details aren't so important here, so I'm kind of brushing through it, minus 3/2 QD squared sine theta cos theta, which is minus 3/4 QD squared sine 2 theta. So, what is the radiation pattern associated with my dipole units? In the phi hat direction. Yes, indeed. So, if I'm doing this, then I'll be radiating with the magnetic field polarized in the phi direction. Okay? And the electric field in the theta hat direction. All right, so what we found now is that the differential, the whole point of this exercise, or at least one of the points, is that to show that this is proportional to sine squared 2 theta, where theta is defined relative to the axis of symmetry. Okay? So here's my egg doing, I won't draw the egg again because I don't want to confuse it. Here's the z-axis. What does the pattern look like if this is a theta equals 0, it's 0. A theta equals pi over 2, it's 0. And where is it maximum?
Pi over 4.
Pi over 4 and 3 pi over 4. So what we have is this flower child pattern. Of electric quadrupole radiation, which maximizes at 45 degrees in each quadrant. So it's a 4-lobe radiation pattern associated with a quadrupole radiation. Okay, to conclude though, I want to say one last thing. What I argued is that the power radiated by electric quadrupole is of the same order as the power radiated by magnetic dipole. They, after all, came from the same order in the power series expansion that we had. Can we see that kind of in these characteristics? Well, the power radiated in electric dipole goes like, well, we have there k to the 6th, right? That's what we got over there. And then we have this quadrupole moment squared, QD squared. Okay? So that's the power. This is the quadrupole moment that we got over there. The power radiated in magnetic dipole let me write this form. Let's call this Q0 squared, which would equal to K6 QD squared. Was what? Well, what we have over there was K to the 4th M naught squared. That's what we had. Right? But what's M naught? Well, M naught goes like the current times the area over C squared. K to the 4th, pardon me. But CT is like lambda. And 1 over lambda is like K. And in the squared, it's like K squared. So this goes like lambda. So this goes like K to the 6th, K squared, squared. All right? So, so the strength of, or the power radiated into these very distinct radiation patterns is of the same order. If the oscillating distribution has both an electric quadrupole and a magnetic dipole that are both changing as a function of time, both will contribute. And in fact, they will interfere because electric fields add linearly. So you have to look at the cross products. In fact, in an atom which has an allowed transition whose selection rules allow for both electric quadrupole and magnetic dipole, both are part of the radiation term of absorption and emission from atoms and molecules. All right. So next time we'll do electric optopole. No.